Test, test, test. Hello, everybody. If you can hear me, please type something in the chat window. Yay, cool. So you guys can hear me. So today I'm presenting from the library of University of Bridgeport. So I'm gonna try to be quiet. If you attended the previous meetups, you will know that I'm not as loud as usual. Well, the reason is because I'm in a library, so I'm trying to respect the rules here. So I hope everybody is enjoying their spring so far, although the weather is not cool. It's cold here in Connecticut today, but yeah, okay. Shh, I'm in a library. I'm gonna try to keep it quiet. So today we're going to talk about evolving artificial neural networks. We were supposed to cover this topic in our 8th meetup, but I was traveling. So now we're covering it in our 10th meetup. So I think it's time to start. So let's go ahead and start our meetup. So before I start, I want to hear from you if you have any cool project. It doesn't need to be related to evolutionary robotics or modular robots. It can be anything, any technical project that you're working on, you're interested in. Please share it with me. We want to hear from you, and let's do this together. So our agenda for today covers an introduction, which will mainly be learning versus evolution. Then we will talk about artificial neural networks, and then evolutionary algorithms, and then evolution in artificial neural networks. We will talk about encoding and representation, different techniques to do encoding, and we will conclude by summarizing the main topics in this presentation. So this presentation was heavily inspired by Evolving Artificial Neural Networks presentation done by Christophe Touchel. I'm not sure if I'm pronouncing the name right, but I'm doing my best. And it's also heavily inspired by Evolving Artificial Neural Networks paper written by Xin Yao, a senior member in the IEEE. So let's start. By the way, today, I'm not going to be capable of reading the questions in the live chat window. So I'm going to pause to read your questions and comments, and then I will continue, because I have only one screen today. Usually I have two. Evolution. Evolution requires a population, often geographically distributed population that displays some variability. Evolution is a process of selective reproduction and substitution. It captures relatively slow environmental changes. I mean, over several generations. Evolution operates on the genotype, which is the genetic specification of an individual. While learning is a set of modifications taking place within a single individual during its own lifetime. So previously, with evolution, we had a population, but here in learning, we have a single individual. Humans display an exceptional capacity to learn. Nowadays, robots have similar capacity to learn. But it takes a very long time to reach maturity. Learning allows to adapt to fast changes in the environment, while evolution will take some time. I'm talking about adaptation here. Learning only affects the phenotype. What is the phenotype? The decoded and embodied version of an individual. Phenotypic changes cannot directly modify the genotype. However, learning can influence evolution, which we call the Baldwin effect. Learning and development interact in an important and non-obvious way. We'll see some examples in today's presentation to understand this in a better way. So the benefits of evolving artificial neural networks includes automating the design of artificial neural network, which can help solving hard problems. The combination of artificial neural networks and evolutionary algorithms can lead to significantly better intelligent systems than on relying on either or, on artificial neural networks alone or evolutionary algorithms alone. So artificial neural networks consist of a set of processing elements known as nodes or neurons, which are interconnected. It can be described as a directed graph in which each node performs a transfer function. If you want to take a look at the details of the transfer function, you can check the paper that I mentioned earlier. I can mention it later, show you the name of the paper, so you can guys Google it and see the details of the function. If you are interested in going through it, we can do that in our next meetup. So the architecture of an artificial neural network is determined by its topological structure, which means the overall connectivity and transfer function of each node in the networks. So let's see. In this slide, this drawing or photo on the right is the human nervous system. And this one here is an artificial neural network. I mean, if you look closely to both of these pictures, you'll find a lot of similarities. Nodes, and here connection, nodes that are interconnected, as we see here. So what are the parameters of artificial neural networks? Connection weights, transfer functions, and topology. So artificial neural networks map an n-dimensional input to an m-dimensional input. They compute a function in an efficient way than other computer architectures do. So let's go through the parameters together. Connection weights, transfer function, and topology. In this example, in Turing EANNs, the nodes or the neurons are two input NAND gates. The interconnections are direct lines or binary switches, or we can call them synapses. The advantage of having Turing EANNs, they are highly efficient hardware implementation. So I don't know if you guys are familiar with Turing EANNs. They call it Turing Unorganized Machine, or TUM, or TUM, which is a machine that make up in a comparatively unsystematic and random way from some kind of standard components. So that's a drawing of Turing machines. As you can see, the nodes. Can you see here the architecture in this drawing? The connection weights should be displayed here in these small boxes. The transfer function, I think I'm missing it in this diagram here. I can see the topology very clearly in this drawing. So there are at least 3 levels where an evolutionary process can intervene during a network construction. The architectural level, or the interconnections, the configuration of the interconnection switches, whether it's enabled or disabled, and finally the initialization of the node values. So learning in artificial neural networks can be divided into supervised learning and unsupervised learning. The supervised could be corrective learning or reinforcement learning. The supervised learning is based on minimization of an error. Learning is based on the correlations among input data. Reinforcement learning is a special case of supervised learning where the exact output is not known. So here, the EANN is learning what to do. Corrective learning, the magnitude of an error together with the input vector, determines the magnitude of the correction to the weights. So let's move on to evolutionary algorithms. Evolutionary algorithms is a class of population-based stochastic search algorithms inspired by natural evolution. Individuals compete and exchange information in order to perform certain tasks. Evolutionary algorithms are good for complex and hard problems with local minima. Fitness functions are always required for almost all algorithms, but EAs do not depend on gradient information and also work with non-differential error functions. So this is an illustration of a genetic algorithm. We start by having a population, and then a selection process takes place. Then mutation takes place, followed by recombination, in order to generate a new generation, or a new population as they call it here. We can actually go through genetic algorithm in one of the next meetups, probably our next meetup, if you guys are interested. Evolving artificial neural networks. What can be evolved? The connection rates, architectures, and learning rules. So these are the things that we mentioned earlier that we are going to go through them. So now we will see how to evolve connection weights, how to evolve architectures, and how to evolve learning rules. But first, let's read this together. It is better not to employ EAs at all possible levels: architecture, weights, and learning rules of evolution. So I'm going to ask you here, why do you think that is not a good practice? And I'm going to pause to read your answers for 1 minute. Let's do this. Oops, so Naveen said he can't see the slides. I hope you can see them now. Cool, Stefan and Kevin, they can. Naveen's still trying. Okay, I don't know what browser are you using. Just the video quality settings. Okay. Yeah, guys, if you have any problems, like if the problem happens more than once, please let me know. So I might change the settings from my side. Okay, any ideas why it's better not to employ EAs at all possible levels of evolution? Okay, so personally, I don't know the answer yet. I'm looking around, I'm reading papers, doing my research, trying to find an answer, and I would love to hear from you. Maybe today at the end of the presentation we can reach an answer. Maybe in one of the next webcasts. So let's move on. Encoding techniques. So Miller have classified encoding techniques into two categories: direct encoding, or strong specification schemes, indirect encoding, or weak specification schemes. Robert and Torrega proposed the third technique, which is intermediate representation. It might be known as grammar encoding scheme. It can be used in L systems. So let's see. Representations. We have binary representation. Connection weight is represented by a number of bits with a certain length. Binary representations are simple, and easy to use when it comes to crossover mutation and hardware implementation. We have real number representation. A connection weight is represented by a real number, and traditional binary crossover and mutation can no longer be used directly in this case. The evolution of architectures. Architecture design is still very much a human expert's job. Therefore, there is no systematic way to design near optimal architectures for a given task automatically. The evolution of architectures involved decoding each individual in the current generation into one architecture. Train each artificial neural network with a decoded architecture by a predefined learning rule starting from a different set of random initial connection weights and parameters. Then compute the fitness of each individual, and then select parents from the population based on their fitness. And finally, apply search operators to the parents and generate offsprings which form the next generation. The evolution of learning rules. Decode each individual in the current generation into a learning rule. Then construct EANNs with random architectures and initial settings, that's a typo, and train them using the decoded learning rule. Then evaluate the fitness of each individual, which is a must. Then you can select the parents based on the fitness values in order to generate offsprings using mutation and crossover. So what are the differences between evolutionary training and gradient-based training? Evolutionary training can handle global search problems better in a vast, complex, and non-differentiable surface. Evolutionary training does not depend on gradient information of the error function. It can be very slow in comparison with fast variants of gradient-based training. Hybrid training. So most EAs are rather inefficient in fine-tuned local search. EAs can be used to locate a good region in space, and then a local search procedure is used to find a near optimal solution in this region. So this is the general framework of evolving artificial neural networks. As you can see here, the evolution of connection weights proceeds at the lowest level on the fastest time scale in an environment, determined by an architecture, learning rules, and learning tasks. However, the evolution of architectures can also be at the lowest level if there is less prior knowledge available than about the connection weights. So knowledge here can be encoded to reduce the search space. In conclusion, separating the evolution of architectures and that of connection weights can make fitness evaluation inaccurate and mislead evolution. It's better use simultaneous evolution. Global search procedures such as EAs are usually computationally expensive. Possible acceleration could be evolutionary hardware. Evolution can be introduced into EANNs at many different levels. Evolution of the weights is useful when gradient information of the error function is difficult or costly to obtain. Evolution can be used to find a near optimal EANN architecture automatically. Evolution discovers possible new EANN architectures. So from an engineering point of view, the decision on the level of evolution depends on what kind of prior knowledge is available. And most solutions are problem specific. So that's it for today. I tried to keep it short because, again, I'm in the library and I don't want to talk too much in a loud voice. So please, if you have any questions, go ahead and type them in the live chat window. And if you have any recommendations for the next topic that we can cover in a week or two, please share them with me. And I will be happy to go through your suggestions. I think at that point we can cover genetic algorithms, probably next week. If you guys agree with me, just let me know. So Stefan said, the question of where and when not to apply evolution in an artificial neural network. He said it depends on the knowledge of the problem domain. Yes, that's absolutely right. Let me just. It was mentioned here, yeah, it's always depend on what kind of prior knowledge is available. Also, the expected results and hardware as EAs are more computationally expensive. You're absolutely right. So excellent. The answers to that question was mentioned twice, once in the conclusion and now by Stefan, which means that the main concepts of today's presentations are already grasped. So that's good. I'm happy to hear that. You're absolutely right. Until we can figure out general intelligence like the brain, you're absolutely right, Stefan. That's why now we see a lot of researchers who work on cognitive computation, but it's still too early to figure it out how to make something similar to a brain or human intelligence. All right, I think it's time to wrap up. It was great meeting everybody again. So I'm gonna go ahead and finish this live stream, stop the broadcasting before getting kicked out of this library. Have a wonderful rest of the day, everybody, and see you in 2 weeks, or maybe sooner, who knows. Thank you very much, Stefan, and everybody, Kevin, Naveen, and the rest that I can't see your names. Thank you very, very much for staying here with us. Have a wonderful rest of the day. Thank you. Bye-bye.